Okay, hi, it's Miss Molesbury here. We're going to continue the word problem fun with distance problems. So you probably have done problems related to distance, even if you haven't really thought about what equation you use. But usually the distance equation you've typically done in the past is going to be that our distance is equal to our rate times our time. So usually, like say we're going 50 miles an hour and we're gonna drive for 3 hours. 50 times 3 would tell us we're gonna go a total of 150 miles. So that's probably some of the basics of how you used it. Since we are in our rational unit, we can actually divide here and isolate a variable to create a rational equation that has fractions. So all of these equations related to distance are going to have a version of distance over rate equals time. So we might have a scenario as simple as this, or we might know if the time it takes to get two different places is the same, we might set the distance over rate equal to another distance over rate. I'm just trying to think of all the possible scenarios I can think of. The other option is sometimes we have multiple parts to a trip in these questions, and so we're going to say that the first part of the trip and the second part of the trip together make the total time. So these are just three scenarios of how the equation might be set up, and we won't actually know till we read the question which one is necessary. So we're going to do these two, and then I did make one more inverse variation question since the first video only had one example. So let's look at number 4. Garth can row 5 miles per hour in still water. This means without any help if the water is completely still. It takes him as long to row 4 miles upstream against the current as 16 miles downstream with the current. How fast is the current? Okay. So think about, we need to talk about upstream versus downstream. Downstream is good. Look at how much faster he's going. He's going 16 miles in the same time that it would take him to go 4 miles against the current. So a couple things we need to label. Whenever you're going upstream against the current, we're moving slower than when we're going downstream with the current. That's when we're going faster. Okay, to decide our setup, let's read the question. It says, how fast is the current? So the current is, the speed that the river is pushing him. Or I don't know if he's in a river or if he's in a stream or whatnot. But there's current in this water. So X is going to be the speed of the current. Okay, I'm going to look at all my pieces of information. I have 5 miles per hour. That sounds like a rate. And then I have two different distances. I have 4 miles and 16 miles. There's no time mentioned here. Also notice there's no total amount of time. So I'm going to focus on the words here that say it takes him as long to row. So the time here is equal for the two parts of this trip. So I think what it's saying is our upstream time is equal to the downstream time, even though he's going two different distances. And now I'm going to look at the problem. Since I don't know time, I'm going to replace the time with distance over rate. So upstream, it says he goes 4 miles, while downstream, his distance is 16 miles. So we're using a version here. We're saying distance over rate. It's really this middle scenario right here. The two parts of his trip take the same amount of time. And now let's think about his rate. We know that typically he goes 5 miles per hour, if it's just him rowing. But now we have to account for the current. If he's going upstream, he's going slower. So let's think about, he's not going 5, he's going 5 minus whatever the current is doing to his pace. When he goes downstream, which is faster, the current gets to help him. So he's not just going 5 miles per hour, he's going faster than that. So y'all, this is going to be a common setup on these problems where we have the person minus their current when it's pushing against them, or a person's rate adding the current when it's helping them go faster. Okay, we've now used all the information. This is our setup, and now we get to solve. Okay, so I can see that the least common denominator is 5 minus x and 5 plus x. And so I'm going to go multiply by that through the problem. So 5 minus x, 5 plus x. And so in my first fraction, the 5 minus x will cancel, and I'll have 4 times 5 plus x. In the second fraction, the 5 plus x would cancel, and the 16 will be left multiplying by 5 minus x. And then I'm going to go solve. So I'm going to distribute the 4, making it 20 plus 4x. Distribute the 5, making it 80 minus 16x. And now I'm going to solve. So I'm going to move my 16x and subtract 20 to the other side. So 20x equals 60. And dividing will give me 3. And then let's think, does that actually make sense? 3, could that be the speed of the current? Yes, I think so, miles per hour. So I'm going to label it. And then you could always go check your answer. If we think it's 3, you could go plug it into each side. 5 minus 3 is 2, and 4 divided by 2 is 2. So this side, his time, his distance over his rate would be 2 hours. And on this side, 16 over 5 plus 3, 16 divided by 8 is also going to tell me it takes him 2 hours for this downstream part of the trip. Okay, also that is one common setup on these distance problems, making the two parts of the trip equal to each other when they take the same amount of time. Okay, let's try another one. 5 says a river barge travels 140 miles from a loading dock to a warehouse to deliver supplies. Then the barge returns to the loading dock. The barge travels with the current to the warehouse and against the current from the warehouse. The barge's total time is 20 hours, and it travels in still water at an average speed of 15 miles per hour. Okay, how fast is the current? So I'm going to go ahead and label x is unknown, and it is the speed or the rate of the current. Okay, so let's look at our different pieces of information here. We're given 140 miles, and there were 2 parts to this trip. So it looks like 140 miles is always the distance. And then we have, let's see, with the current and against the current. So we do have, with the current means he's going faster. Against the current would be slower. This one's a little different. We have a total time of 20 hours, and then we have the speed of the barge without the current. So the setup here needs to show our 2 parts of our trip. So with the current, which is going to be faster, and then against the current, which is going to be slower. And when we add those 2 together, it would tell us our total time. So let's try to set up a question like this. Our total time we know is 20 hours. And if time is isolated, it's going to be distance over rate. And we have two parts to this trip. So this is going to be like this third equation we wrote over here to the right. So it looks like the distance is 140 miles each way. So both parts of the trip have the same distance. And then we need to look at their rate. Typically, the barge without any current would be going 15 miles an hour. When it's going faster with the current, I get to put a plus X, showing that its speed is increased by some amount. And on the slower portion, I'm going to do 15 minus X. Okay, this is it. This is the setup. We use the same distance twice because they're covering the same distance, right? They're going 140 miles to get to the warehouse and 140 miles to come back to the loading dock. We showed the different speeds, and then we made it equal to the total time. So let's go ahead and take our equation and multiply by the LCD. I'm going to make this 20 over 1, just so that I don't forget it still needs to get multiplied as well. And our LCD would be 15 plus X, 15 minus X, and let's see what cancels. First fraction, the 140, will multiply by 15 minus X because the 15 plus X cancels. The next 140, its 15 minus X would cancel, so it will be left multiplying by 15 plus X. And then on the other side of the equation, well, nothing's canceling. There's no denominator, it's just a 1. So 20 will get multiplied by 15 plus X and 15 minus X. And that's a step most people will forget, or a common mistake would be to just make this a 20 and think that the problem's going to be awesome. But instead it gets both. It's going to be a little bit more work. We can handle it though. So remember, you can use a calculator if needed. 140 times 15, yeah, I mean, a calculator would be smart. We're going to do, let's see, this is, oops, get a pen. 2100 minus 140x plus, we're going to get 2100 again, plus 140x, so those are canceling. The other side, I'm going to notice that this is a difference of squares. So I'm actually going to multiply that first, right? 15 times 15 is 225, and then the 15x in the middle will cancel, and I'll be left with minus x squared. And now I'm going to go ahead and multiply this out. So 225 times 20 is a 4,500 minus 20x squared, excuse me. I have a 4,200 on the left side when I combine these together. And now let's solve. So up to you which way you want to move different parts of your equation. It looks like there's no x in the middle. So I think I could just isolate this single x here by subtracting 4,500. Let me get a new clean page. So negative 300 equals negative 20x squared. I need to isolate the x squared, so divide by negative 20. And so we're going to get 15 equals x squared. So it's okay here, we're not getting a whole number as our answer. When we take the square root of 15, let me get my calculator. 15 square root. We know it's between 3 and 4, and I get that it is approximately 3 and we're going to round to the nearest thousandth, 3 decimal places. So I'm going to say approximately 3.873 and then miles per hour. Because think about what were we actually finding. So go back up if you need to. Let's see, if you need to, where it says the speed of the current, and we can go from there. So we know it has to be miles per hour. Okay, we are going to go ahead and do one more word problem. Let's see, it says the time it takes you to drive to vacation varies inversely with the speed you drive. If it takes you 3 hours driving 65 miles per hour, how long will it take if you drive 75 miles per hour? I should have put a question mark at the end here. All right, so varies inversely. This was from the last video, but that tells me my equation is going to be y equals k over x, and k is the constant of variation. And our first goal is going to be to find k. These words right here are also your key phrase to tell you what's x and what's y. So y varies inversely with x. So whatever comes before that phrase is y. So the time it takes you to drive to vacation is going to be y, while the speed you drive is going to be x. Okay, the next statement gives us an x and a y. It says if it takes you 3 hours, so 3 hours is a y, it's a time. So I'm going to plug that in for y. And you're driving 65 miles per hour, that's an x. Whoops. So finding k. We're going to be able to find k and then answer the follow-up question. So times 65, I get 195 for k. And remember, that's important, but it's not my final answer. So now I'm going to go over and do y equals 195 over x. And now I can answer the follow-up question. How long will it take, so what will the y be if you drive 75 miles per hour? Okay, so that's an x, so we're just going to go plug it in. 195 divided by 75. Let me get my calculator. 195 divided by 75. 2.6. So 2.6 hours, and that would be an acceptable answer. We could convert it into hours and minutes if we wanted, but that's not really the point. So 2.6 hours would be our solution. It makes sense that it's going to be a shorter amount of time because we're driving faster. So we knew it had to be less than 3 hours when we were driving 65 miles per hour. Okay, y'all, so you should be ready to do both a word problem practice page you're going to get and also complete the last section of the spiral review that is full of fun word problems. Please let your teacher know if you have any questions.